There you go. All right, so we're recording this for Andrew. He's going to be giving his senior project talk until 7, so he's missing out on some of the lecture.
Is that why everyone's here today in art class?
Yes, yeah, it's pretty crazy. I really wish that, you know, it wasn't conflicting with our class so we could actually go and enjoy it, but the bike
That's awesome.
is pretty cool. I didn't really get to look closely, but I saw a bike, which was pretty cool.
He totally built an electric bike.
That's sweet.
He used the physics for the drivetrain. He was talking about the physics. I was like, hey, wait, I saw it around here.
Oh man. Well, I'll have to. See, that's why I'm sad that I get to have to miss that.
I'm happy Andrew's not here because I'd like to watch this video multiple times.
We could also, you know, class field trip down.
We could if we didn't have so much to do.
Yeah.
Yeah. Okay, so the plan today is we're going to do our concept review from lecture 8. Then we'll be doing lecture 9, and then we're going to review for the final. Yeah. No lab, obviously. Okay, so the worksheets are up here if you want to follow along on the multiple choice questions. We've got one question from chapter 39, because we did that one section from 39 about black body radiation. So if you increase the temperature of a black body, what happens to its, well, let's see, wow. Which choice is accurate? There's lots of things going on here.
It's sort of a mistake. That's sort of weird.
It's definitely tricky. Yeah.
I think
Like as you have increasing temperature change, these go up. I know they get shorter. I'm just not overthinking it.
Well, how many people think they have an answer ready?
Sure.
isn't it all
Okay. Well, yeah.
It should be big. It should be confidence, but.
Well, I'll admit that the answer when I first looked at this was a non-confident answer, and I had to check the answer, and then I was like, oh, okay. So, okay, who thinks the answer is A? 1, 2, 3, 4, 5. Okay, who thinks the answer is B? 1, 2, 3, 4. Who thinks the answer is C? 1. All right, who thinks the answer is D? All right, who thinks the answer is E? All right, so I think it went, was it 4, 3, and then 1 for A, B, and C? I think A, or was it 5?
5, 4.
5, 4, 1? Yeah, that's what it was. All right, so A and B were getting the most votes. So whoever chose A, tell us why you chose A. Justin?
So, I vaguely remember an equation regarding black bodies where the radiation, or the intensity, I think it was the Stefan Boltzmann constant,
Uh-huh.
temperature in Kelvin to the 4th.
Okay, and what does that tell you?
That as the temperature increases, more radiation is increased, but there's nothing to do with wavelength. So both the short wavelengths and the long wavelengths would be more.
Okay, okay. Did anyone else use Justin's line of reasoning?
Yeah, I agree with that.
I just used the equation for the black body radiator, which just shows it does have wavelength in the equation, sits in meters Kelvin. That seems like it will increase regardless of the value of lambda.
Okay.
So
Can you just, I don't remember what it was. Can you just tell me the,
it was lambda. Oh, but it's peak lambda, so maybe that's different.
The one you're having on there right now is 2 pi hc squared divided by lambda to the fifth, and then in parentheses you've got e with to the hc over lambda kt minus 1. It's gross.
I was meaning to ask you about this. Is that natural log E, or is that charge of an electron?
that's natural log E. That's exponential. Exponential.
Yeah, that was my question.
Yeah, I mean, if you look at the graph, it's got a weird shape, but the right-hand side of it looks kind of like exponential decay, so that's maybe a reminder that that's the exponential function. Anybody else who chose A want to weigh in?
Well, I like his explanation with the formula, but I was just thinking of the graph where as the temperature increased, it would shift to the left, but overall it would be taller at, yeah, like that.
So this is T low and this is T high.
Right. And so I was thinking, the peak would have a lower wavelength, but overall there would be a higher intensity at both ends of the wavelength spectrum.
Okay, did anyone use Ian's method of thinking about the graph? That was the way I used, was the graph. Have we covered all the methods to get to A, or is there anything else?
So I guess a clarification. Does intensity, is that synonymous with radiation in this context? Or is that a different magnitude that we're looking for?
Radiation, we learned, is measured as a function of power. So when we learned about thermal radiation in 222 when we did thermodynamics, that was power, which is units of watts. And intensity has watts. It depends on which equation, right? One of these was intensity per meter, and one of these was intensity per cubic meter. Isn't that right? That they had different units?
The first one is
I think they're going to be per square meter for both.
per meter squared times k to the 4. Yeah, I think it's the same between those.
But I'm remembering there was difference in units in the denominator, but it's related to power. So in fact, if we go back to our general form of intensity that we've used all term, we had intensity was equal to power over surface area. So radiation is power, intensity is sort of radiation per surface area. If that helps.
So then what is the magnitude for the black body radiator one where it's like lambda sub n times the temperature, and you get units, meters, or no, yeah, I think that's, unless I wrote this down wrong, I think it's meters per thousand.
Right, that's just a constant that you get. That's not solving for a variable. That's just defined as a constant value. So the maximum wavelength times the temperature gives you a constant. I'm trying to find those lecture notes wherever they went.
So are we A?
Well, that's A. That's A. If everyone's done talking about A, why don't we give people who chose B a chance?
Okay, I thought of that graph too, but I kind of thought of this question in terms of relatively. I understand that the radiation across all spectrums will increase, but it becomes more biased to the shorter wavelengths and less biased to the higher wavelengths. So, I can see A or B being right, it just depends on like what they're thinking of exactly when they ask the question.
Yeah, and I think that's what makes this more kind of a trick question, in that without actually solving for values, I could definitely see where you're coming from, that we've never actually verified that the right side of that peak is, I guess, quantity-wise, that there's more area under here than there is area under here. I don't know if my drawing is accurate, but I could see where you're coming from on choosing B. Did anyone else who chose B use the graph to support their thinking? Same logic Jordan used? Okay. Okay, and C, Jacob?
I use the same logic as Jordan, I think I just had it reversed.
You had it reversed, okay. Well, let's find out. The correct answer was, in fact, A. So good reasoning for everybody, but again, this is sort of a tricky question in that we can make assumptions, and if you make the assumptions that we've made for case A, that this increase in height is going to mean that there's more area on both the right side and the left side, that assumption is correct, but we've never actually verified that, which makes it sort of a tricky question to ask. Okay, so going back to chapter 38, the rest of the questions are from 38. In an experiment to demonstrate the photoelectric effect, you shine a beam of monochromatic blue light on a metal plate. As a result, electrons are emitted by the plate. If you increase the intensity of light but keep the color the same, what happens? I don't know about you guys, but I really like that PHET simulation. Actually, in hindsight, I think next time I teach this class, I'm going to put the PHET simulation the week before I teach it, because I think it's a good one to learn the photoelectric effect, and it's easier to understand visually than me trying to stand up here and explain it in words. So I think the next time I do it, I'm going to have it be more of like a mess around with the simulation and figure out what's going on and try and explain it, and then we'll come to class and learn about it. So, all right. Okay, who thinks the answer is A? 1, 2, 3, 4, 5, 6. Who thinks the answer is B? 1. Who thinks the answer is C? 1, 2, 3. Who thinks the answer is D? Okay, so we'll start with A because I had 6 votes. Why did people choose A?
I'm not sure if it's, I know that more electrons are emitted per second just from reading the book and also working with the simulation, but I don't remember about the kinetic energy being increased.
Justin? Justin says he does.
Energy
Just
doesn't
K
change.
equals
Yeah.
1/2.
Energy doesn't change.
Increasing the intensity doesn't increase the current.
Yeah.
So you just,
Oh, shit.
energy's the same. You just
Increasing the intensity does increase the current.
Increasing the intensity does increase the current because you've got more electrons flowing,
Yeah.
but it doesn't change
Kinetic
the kinetic energy. Yeah.
Because it's an equal.
Yeah.
E is equal to H,
So my notes are
H times C over
The intensity is not in that.
It's good to know now.
So the total energy doesn't change from each electron has the same amount of energy.
Yeah, so every electron emitted has the same amount of energy, but you just get more electrons if you increase the intensity. And if you're not using the right color light, there might be a certain wavelength where you just don't get any electrons to get emitted. So it doesn't matter if you're using a color that's got too low of a wavelength, you could blast it with light and nothing's going to happen.
Yeah, using platinum on the simulation, like jack me up, I'm all up in the colors going, there's nothing here.
Nothing
It's all
happening.
ultraviolet.
Yeah.
Okay, maybe I should have chose something else, but no, I'm sticking with it. It was weird.
Yeah.
Because it wasn't color, but color that didn't matter.
Maybe somebody has some thoughts on this, but I was thinking, maybe that's a good thing, because if your platinum ring is emitting electrons every time you're out in sunlight, maybe that's not such a good thing.
Personal hand buzzer.
I don't know. Maybe I'm like thinking about it all wrong. Maybe that like it emitting electrons isn't that big of a deal.
If you do with electronics, it could be because you fry stuff. Yes.
Yeah, that's true. Jacob?
Was there an equation that talks about how much current was traveling through the circuit?
No, we
Intensity
didn't.
of light or anything?
We didn't delve into that. Yeah, there probably is, but it wasn't something we looked at. Yeah. Yeah.
I think you might have a silly question, but if that didn't say the maximum kinetic energy, would it be C? If it was just, there'd be some KE change? Because we say the maximum?
So the kinetic energy was derived from the total energy, right? So your electron, it's in this electron well when it's trapped within its atom. And in order to escape, let's say it's down here and a photon hits it of a certain wavelength. And let's say it gets enough energy to escape. It's going to use up some of its energy to get to this height. And that's the work function. And then whatever it has on top of that, that's its kinetic energy. And so the total energy, E total, am I doing this right, or is this right? E total is kinetic energy plus the work function?
Yeah, because you get the kinetic energy, that's the line equation. The y equals mx plus 2. The work function over E, and then kinetic energy is the hc over lambda. Because you get frequency.
Times the frequency, yeah.
Yeah.
I thought this was H times F. And then kinetic energy was, well, I know it's 1/2 mv squared, but I think it had another form.
K max equals H times F minus the work function.
I'm just trying to remember, because I'm just pulling this out of my head because my lecture notes, I didn't actually print off last week's lecture, so I don't have the benefit of the lecture notes at my disposal, but I can look them up on my thumb drive.
Yeah, the energy of a photon equals H times F. The K max is H times F minus the work function.
Okay, so K max was just, okay. It's just a rearranging of the same thing. Oh, EV naught, that's what that's the other form of it I was looking for.
Right.
Okay, so HF equals EV naught times the work function. That's what I was looking for. So HF is also HC over lambda. So the amount of energy, and so energy total would be all of this. From here all the way up to here would be E total. So however much energy the electron gets is directly related to the wavelength of light. And so if you're not changing the wavelength of light, you're not changing this side of the equation. And you can't change the work function because that's dictated by the type of material it is. This well is the same for every atom inside that material. So the work function stays the same. And then, so if these two terms are constant, then this one has to be constant, not dependent on wavelength. Yeah, so if you change the intensity, it's not going to change any of these three terms. Yeah, good question.
Voltage source and that, the potential of the voltage source, and that's obviously going to change the...
No, this isn't your voltage stroke. This is the stopping potential. So this isn't how much voltage you're driving through the circuit. This is a very specific voltage at which point it stops the electron from reaching the anode. So that's not you. You don't just get to pick this arbitrarily. This isn't whatever voltage source you add. This is a very specific value where if you tune that voltage correctly, you're going to tune it just to the point where the electrons are fighting against the electric field and they just stop reaching the anode. So your current goes to 0. And so that's a very specific voltage. It's not something you get to pick. It's specific to the material.
Right, but you still, in the simulation, you have control over.
You get to control the voltage, but what you're controlling is what voltage do you get to the stopping potential. So you didn't decide the stopping potential, it's decided by the material.
I see what you're saying.
Yeah.
And the wavelength of the light.
And the wavelength of light, yeah.
So that's always going to be constant as well.
Yeah. Yeah. So yeah, I think what we can say is since intensity doesn't show up here, then intensity is not going to affect the kinetic energy of our particle. Yeah, good questions all around. Okay, this graph shows the stopping potential as a function of frequency of light falling on a metal surface. If a different type of metal is used, what would happen to the graph? Okay, who's ready to vote? I feel like people are ready. Okay, who thinks the answer is A? Who thinks the answer is B? Everybody. C? Nobody? D?
I'll just see.
Devil's advocate.
Double, okay. 1 vote for C, 2 votes for C. Okay, so most people chose B. Why did you choose B, the folks that chose B?
This is a constant.
The slope is a constant? Do you guys remember what the slope is always? H over E. And to be super confusing, this is not exponential now. This is the charge of an electron. Yeah. Would it help in this equation if we added a caret? I don't know.
Or the other thing, do
Or if we said
negative?
x.
Just put an E minus.
Yeah,
So it
Oh.
minus an electron.
Or electron?
Like that.
Yeah.
Oh, aha.
That would make sense.
Okay.
That's a weird inverse.
Okay. A photon has a position uncertainty of 2 millimeters. If you decrease the position uncertainty to 1 millimeter, how does this change the momentum uncertainty of the photon?
Oh, I hate Heisenberg.
I honestly did not understand this whole thing.
I'm trying to remember the equation. Heisenberg shocks. He's an alright guy. I'm not talking about Breaking Bad.
No,
The historical one. The story.
No, actually, when I looked at this, I got really messed up because the book answer was wrong at first. And I was like, what? It doesn't make any sense. And then they have where I get these slides from, they have one slide that looks like this, and then the next slide has a little check next to the right answer. So the slide with the check was wrong, but then when I looked at the notes on this slide, it had a different answer. And I was like, but I spent probably 15 minutes cursing at my computer.
this one?
I want to say it's B. So. We're not both on the same side, so it just is.
That changes.
Yep. That's what I'm going
Okay, I think the people have come to a consensus perhaps. Are people ready to vote? Sure? All right, who thinks the answer is A? B? 1, 2, 3? C? D? 1, 2, 3, 4, 5, 6, 7, 8. 8 for D. E? 1 vote for E. All right. So I think that was 3 for B, 8 for D, and 1 for E. So people who chose D get to talk first.
So I remember the relationship is that the more accurately you know one, the less accurately you know the other.
Uh-huh.
So if your position uncertainty decreases, then your momentum uncertainty increases. So it would have to be D or E.
Yeah, that was what I thought too. And that was the only thing the formula I couldn't figure out.
What's the formula you got in front of you?
Is it the one that's with
Delta X, delta P.
Greater than H over 2.
Greater than or equal to.
Greater than equal to.
That would
And
be
this is H bar. It's H bar over 2. H bar over 2.
This H over 4 pi.
I don't know.
It's the silliest thing I've ever heard.
I know. It's not the first, this is delving into like high level physics that we're doing right now. And so as I got higher and higher in physics, the more dumb things like this came up, like the angstrom unit. Like 10 meters to the power, to the negative 10th meters. But it doesn't apply to anything else, only meters. And I'm like, why don't you just write to the power of negative 10? It's like some old guy a long time ago. In fact, a long time ago, physicists liked this like old boys club where they had their own language and they made it intentionally confusing because we're just like, we're gonna be smart and nobody will know what we're doing and we'll look really cool because nobody else does it. Yeah. So, okay, anyway. So this is just algebra. I know the uncertainty thing being less than or greater than or equal to is it leads to a lot of confusion. But the way it's described is, the principle at play, sort of the underlying principle that says we can't know one precisely without knowing the other less precisely. That's sort of like an equal sign, but it has to be greater than or equal because this is humans involved here in measurements. So inherently, we have error in our calculations. So that's the only reason why you have the greater than or equal to sign is your uncertainty in knowing things is always greater than 0 because you can't measure anything perfectly. So I hope that helps. So if you just imagine this being an equal sign, then that will hopefully help you. And then if you think that this term, if this becomes 1/2 as big, 1/2 delta x, then for this side to stay the same, what do we have to do to the delta p?
Double that.
Yeah. Multiply it by 2. And then the 1/2 and the 2 cancel, and then you get the same thing. So.
That makes more sense this time than when you said it last week.
Okay. Well, that's good that we do the review then. It's always, helpful to revisit these topics to clarify our understanding. All right. So let's just verify. Anybody else want to add anything? Okay. Let's just verify the book. Book does say it's D.
The equation made this more confusing to me than the
I like that. Who was the one that said the description? Was that you, Justin, that just said if you want to know something more precisely than that? Was that Ian? That was Ian. Yeah, so you just didn't even worry about the equation and just said the underlying concept is this. And that makes a lot more sense.
Because that's what I was thinking when I looked at the equation. Oh, no, it's over 2 square root.
Yeah. You made phase one, right?
All right. Last one, I think. Is this the last one? Yeah. A photon has momentum uncertainty of something. If you decrease the momentum uncertainty to half that, how does this change the position uncertainty of the photon?
Exact same question with some fancy numbers.
So numbers,
Not even opposite, really.
Hence why I don't even bother saying what the momentum is. It's like something and then half of something. So.
I think we're all in agreement.
All right, we're ready to vote? Okay. Who thinks the answer is A? B? C? D? All right, all right.
I'll try not to justify it.
Okay, so while people were walking out the door last week, I was really quickly explaining double slit interference, so I just want to talk about that a little bit again for people that obviously wanted to get out of here. And then we'll talk about